Okay. So, hello. So, thank you for joining this session. So, and also thank you for preparing this workshop for Aran, and Tiago. Yeah. So, my name is Masayuki Ishikawa from Sony in Japan. I'm going to be here because it was my first visit in Brazil. And actually, it was very long flight from Tokyo to this Campinas. Maybe it took almost 36 hours when I left my home for Brazil. But anyway, today I will talk about running NuttX with VirtIO, so VirtIO on QEMU. And QEMU, is, perhaps you might know, it's a famous open source processor emulator which can run NuttX. And last year, I also talked about QEMU, but this presentation is very different. And before starting my presentation, let me introduce my background. Actually, I have several technical backgrounds, so including embedded systems. As you will see in this slide, so I introduced Linux, Android, and the NuttX to our audio products before. For example, this 8800 is the first generation Linux-based platform, portable media player released in 2007. And this DX1 is the third generation Android-based portable media player released in 2013, and supporting also high resolution audio. And this UX560 is the first generation NuttX-based digital voice recorder, so released in 2015. I gave this product to Alan as a gift when we met in America in 2018. And since 2016, I've been joining several conferences such as ELC, Embedded Linux Conference, and NuttX online workshop, and talked about how we applied NuttX to our products, and discussed feasibility studies such as SMP, symmetric multiprocessing, and networking. And if you are interested in my presentation, you please visit the ELC website and the NuttX channel on YouTube. So here is today's agenda. So first, I explain what VirtIO is, and also talk about my motivation for this work. Then I introduce the VirtIO architecture in QEMU, VirtIO driver implementation in NuttX, and VirtIO networking with QEMU. I also teach how to run VirtIO with QEMU, plus hypervisors such as Linux KVM and Apple Hypervisor Framework. And finally, I will show demo videos. So what is VirtIO? So when I wrote this slide, I asked this question to ChatGPT Plus, and the answers was like this. The key point is it's a standard interface, and we use within QEMU and KVM virtualization platform, and presents a simplified generic device. This is very important. And the guest OS requires the VirtIO drivers. Popular VirtIO drivers types include network and block device, block storage. And if we write a figure so based on this answer, the figure would be like this. Here, KVM is a kernel-based virtual machine. It's an open source module in the Linux kernel that allows kernel to function as a hypervisor. Of course, we can run VirtIO without hypervisors, but yeah, this slide shows with hypervisors. And KBA was originally designed for x86 processors, but also have been ported to several CPU architectures, including ARM. Of course, you can also find more information about VirtIO from this actual official wiki. And before explaining my motivation, let me introduce my presentation at NuttX 2022, so last year. In this talk, I explained how to run NuttX with MMU, Memory Management Unit, on QEMU, and discussed these kind of build types, such as flat and protect and kernel. So running NuttX with MMU is very similar to run Linux. Also, I presented a demo video regarding Sublet 6 port with QEMU, which has quad Cortex-A9 processors with networking. And however, we could not use networking for RISC-V or 64 platforms at that time. So this slide shows my motivation to hold this work. So before implementing the VirtIO drivers, only some configs supported networking with target-specific drivers. Also, QEMU ARM B8A processor and RB-BERT configs did not support broke devices, but HostFS works with semi-hosting, and thus only running simplified use cases such as N-shell and SMP multiprocessing environment. And after implementing VirtIO drivers, so you can run more complicated scenarios, such as Telnet, iPerf, and MK-FATFS, so with QEMU, B8A, and RB-BERT RISC-V configs. Also, it would work with QEMU plus hypervisors, such as KVM, so Linux KVM, and Apple hypervisor framework. On actual ARM64 hardware, for example, Raspberry Pi 3B Plus and this MacBook, M1 MacBook. This slide shows the VirtIO spec history. In 2012, Virt 0.9.5 was released. The spec was still in draft version, and only PCI transport was defined. And some device types, such as network and broke device and MM transport, are declared in the appendix. In 2016, version 1.0 was released. In this version, some device types, such as network and block, were officially supported. Regarding transports, the PCI and MMIO and channel IO are officially supported. Here, channel IO is used for IBM mainframe machines, which I've never used before. In 2019, version 1.1 was released. In this version, some device types such as socket, crypt, and IOMMU were newly added. And last year, so version 1.3 was finally released. In this release, new devices such as audio, so, video encoder, a video decoder, and I2C were supported. And last month, the change freeze for version 1.3 has been done. So this slide shows the VirtIO support status, which I investigated with latest QEMU source code. In the VirtIO spec 1.2, there are many, more than 40 device types. However, only some of them are supported in QEMU. And for example, network and block devices are supported, but video encoder and video decoder are not supported by the QEMU at this time. Also, some device types such as I2C and GPIO are supported by the vHost user backend. In today's talk, I will not explain what a vHost user is, because it's more complicated to improve on performance inside QEMU. As for the bus architecture, QEMU supports all device bus types in the spec. From this slide, I explain about VirtIO architecture in QEMU. As you can see in this figure, QEMU runs on the host user space. In guest OS, in this case, NuttX is guest OS. There are front and virtual drivers. The purpose of these drivers is to enable guest OS to interact with virtualized I/O devices on the host efficiently. And inside QEMU, there are backend VirtIO devices that emulates our hardware and interface to our host resources. Also, they optimize the performance for guest OS interactions. To facilitate communication between host and guest, VirtIO, so we use the VirtIO. Now, with this structure, we can transmit data and control messages efficiently. We also use bearing, so which is a shared memory structure, organizing the buffers for communication, conducting containing a descriptor and available and use rings. So regarding bearings, VirtIO defines 3 kinds of bearings: bearing desk, bearing abel, and bearing used. Bearing desk defines data buffer structures, including memory location and sizes. Bearing abel is used to signal available buffers from the guest to host and notify the data of a new data, notify the device of a new data or I/O requests. For example, when sending your network packets, we use this bearing abel. And bearing used indicates buffers that device has finished processing. For example, for receiving network packets, we use this bearing used. In the next slide, I will explain example or descriptor as bearings. So I borrowed this example from our website again. In the descriptor table, 4 entries exist in this specified buffers. The first 3 entries are writable. So you can see this W bit is specified here for 3 buffers. And second and the third entries are changed with this N bit. In the available link, IDX equals 3 shows the 3 descriptors are now available to the device. Here, please note that we assume that the previous index was equal to 0. In the use ring, IDX equal to shows that 2 descriptors have been processed by this device. As a result, the first descriptor has filled with 0x50 bytes. And second change descriptor was filled with 0x350 bytes. And next slide shows VirtIO implementation history in NuttX. So I started to implement the VirtIO MMIOnet driver from scratch almost a year ago. The implementation was straightforward. And finally, my pull request was merged last November. And I tested the VirtIO network driver with RISC-V and ARM64 on QEMU. Then I added RBVirt K NetEnsure 64 and RBVirt K NetEnsure 64 SMP to test a VirtIO network driver with RISC-V MMU environments on QEMU. And after that, I added the VirtIO block driver, so which implements block drivers. Also, I added hypervisor support, which can run on ARM64 hardware such as Raspberry Pi and Apple M1 MacBook Pro. And after my block device driver was merged, Xiaomi members sent a new pull request, which supports a new VirtIO framework. And I was asked to review this PR, so in which I pointed out several bugs and performance issues. The PR was finally merged last month. So the latest code is much different than from my original implementation. From here, I will explain my driver implementation. As I explained in the previous slide, please note that latest source code, latest code differs significantly from mine. So first of all, so we need to understand VirtIO registers for MMIO. As you can see in this header file, so there are many registers. In this talk, I will not explain all of registers, but explain some critical registers in these red parts. The first register is magic value. In the spec, the value is defined like this. So we need to find this value in the order of the VirtIO space. The second register is a version. The version is used to distinguish the legacy devices. In my implementation, the version number is checked. And the third register is device IO, which we use this register to identify the device types described in the spec. So for example, so VirtIO for the network card is defined to 1 in this chart. And as I explained in the earlier slide, so we use VirtQ to communicate between the front-end driver and the back-end device. And if we use multiple VirtQs, we need to use this Q cell register to select which VirtQ is used. Another important register is in this figure is Q notify. So writing a value to this register notifies the device that there are new buffers to process in your queue. So for example, queue notify registers will be written so when sending network packets. This slide shows final figures to explain VirtIO registers for MMIO. However, there are many critical registers to explain. For example, interrupt status and interrupt ACK are used in interrupt handlers to check the status and to notify the device that we handled on interrupt. QDisk and QDisk low and QDisk high registers are used to specify a physical address of the descriptor table, and the the driver low and the Q driver high registers are used to specify a physical address of available ring in the previous slide. And also Q device low and Q device high registers are used to specify a physical address of use ring in the previous slides. From this slide, I will explain VirtIO related drivers. So first one is VirtIO MMIO.c. In VirtIO MMIO init, it explores all of the VirtIO MMIO space, which depends on board configuration. In this figure, it calls following VirtIO dep init. In VirtIO dep init, it checks magic number and version numbers. And when I explained in the previous slides, please note that we need to specify a global VirtIO MMIO, so fourth option for QEMU to work with version number checking. Then it checks our VirtIO device types. And for example, if we find a VirtIO net device, it calls VirtIO MMIO net init. And if we find a VirtIO VLK device, it calls a VirtIO MMIO block init respectively. The next slide shows Vert MMIO net.c, which implements our network driver. In VirtIO net initialize, it allocates Vert queue for RX and TX. Then prepare empty buffers for RX. And according to spec 5.1, it says that empty buffers are placed in one Vert queue for receiving packets. And also, please note that we use one writable descriptor for RX. In VirtIO transmit, which sends network packets, so we use two change descriptors for TX. They are header descriptor and packet descriptors. For more information, please see spec 2.7.4. Technically, we can use only one descriptor for TX. Actually, Xiaomi's latest implementation uses one descriptor to improve performance. But we need to implement a network driver that supports IOB offloading. In the VirtIO transmit set first descriptor and in the available lane and calls memory barrier and increment available check IDX and notify the backend by writing the TXQ number to the Q notify register, which I explained before. So I need to explain more about VirtIO net driver. In VirtNet interrupts, so which implements interrupt handler, it disables further interrupt first and checks the interrupt status registers and set the interrupt ACK register, so which I explained in the previous slides, and then call work queue. In botnet receive function, so which is called from the work queue handler, so it checks newly added descriptors, so based on use IDX. Then receives a packet and call VirtIO RX dispatch. Then update RX available link and increment RxQ available index and update RxQ last use links. And for more information on receiving use buffers, so please refer this 2.7.14 in the spec. And following slide shows VirtIO network with QEMU. There are two kinds of networking modes. The first one is QEMU user networking based on the SLIRP library. In this mode, NAPT network address and port translation as being done inside QEMU. The obtained IP address for the VirtIO network driver is on NuttX is assigned to 10.0.2.15, and default gateway is assigned to 10.0.2.2. On the other hand, IP address for the host network driver on the host OS depends on your network. To access Telnet daemon, so we need inside NuttX, so we need to use a port forwarding. The following QEMU options shows user mode networking, so with the NetDep user option, and port forwarding with host for FWD option. The minus device VirtIO net device option shows we use the VirtIO net backend on QEMU, so which associates with the user mode networking by ID. And another networking mode for is QEMU is bridge networking. In this model, so we use a tap driver on the host OS to make a virtual bridge between in the host driver and the VirtIO net driver on NuttX. To use this mode, we need to specify NetDep bridge for the QEMU option. In this mode, we do not use port forwarding, and IP addresses on both sides, NuttX and host side, depends on your network. So finally, I explain about the MMIO BLK.C block driver for VirtIO. In VirtBLK initialize, it creates one VIRT queue and obtains a capability from config register. And regarding the capacity info, the spec 5.2.4 device configuration layout says it is explained in 512 bytes sector. It's okay? Oh, no? Okay. When sending a request, it sends a first descriptor. This is a chain descriptor for read and write operation. They are header and sector buffer and status. And in a read operation, so flags for the status and the sector buffers are writable. When sending a request, it sets the first descriptor, and so when which is a header to the VirtIO Abel, and issues a memory barrier and before updating Abel index, and then increment the Abel index in the VirtQ and update our Q notify to notifier block and backend, and finally wait for completion. So this slide shows QEMU command and options. The first one is ARM64 specific commands and options, so without hypervisors. So QEMU command is QEMU system ARM64. So we need to specify CPU and machine options, and in which we have to use virtualization on, and DLC is version 3. I'm still unsure if we can remove these options, virtualization and DLC options, but we need to specify so far. The next one is RISC-V specific commands and options. For RISC-V, there are two kinds of QEMU commands. So one is used for 64-bit and other is 34-bit. In both cases, we need to specify machine options, so BERT and ACL in on. So here, so ACL is a RISC-V advanced core local interrupter, which I added to run Linux in SMP in supervisor mode last year. And various option means that we don't use Open SBI supervisor interface firmware. And to support block device, so we need to specify following options. For example, a driver option is used to specify my disk 1GB.img file in raw format image. And device option is used to specify block device by which with the driver. So regarding the network related option, please refer to the previous slides. And common option like this. These options mean that we do not use the display and run NuttX in SMP mode. This slide shows how to debug the QEMU. The first one is a very typical debugging with the GDB servers. So for example, this GDB TCP, 1, 2, 3, 4, 5, that QEMU listening for incoming connection from GDB on TCP port 1, 2, 3, 4, 5. And -S, as capital S option will make QEMU not start a guest until you tell it from GDB. The second option one is how to capture the dump packets. So usually you would use a TCP dump or Wireshark on a host machine. However, QEMU provides another option to dump the packets like this. So with this object, so filter dump option. And third one is another command for so-called monitor commands. To enter the QEMU monitor mode, we need to use Control A plus C. There are many commands in this mode, but regarding the VirtIO, the following info command might be help you. So far, I've discussed how to run the VirtIO QEMU, but it does not use hypervisors. In this slide, I discussed how to run VirtIO QEMU plus hypervisors. To run NuttX with hypervisors, I created two configs, such as QEMU, VirtIO, NuttX HV. So this means the hypervisors. And QEMU, I am VirtIO NetShare SMP hypervisor, so with SMP option. And so running QEMU with hypervisor will improve the performance. Then running QEMU running QEMU in emulation mode. As for hypervisors, you can use Linux, KVM, and Apple hypervisor framework. So for example, I've been using Ubuntu 20.04 server on my Raspberry Pi 3B Plus. To run QEMU with KVM, you need to use a foreign QEMU option. Please note that we don't use virtualization and GH version number parameters for machine options. And to QEMU with Apple hypervisor framework, I've been using this MacBook Pro for testing as well. This QEMU option is very similar to the KVM version. It's just specify Axel HBF instead of Axel KVM. And this shows the performance comparison with hypervisors. So first chart shows the get prime performance. So get prime is application to find your prime numbers. Smaller score means high performance. And as you can see in this chart, using hypervisor is almost 5 times faster than without hypervisors. The following chart shows IPAR performance. I tested IPAR in both client mode, so -C option, and server mode with -S option. In both cases, so using hypervisor is almost 2 times faster than without hypervisors. The performance improvement is not as good as get prime cases because get prime is a CPU intensive use cases, and it's easy to improve performance compared to IPAR because which need to more interaction with drivers. And this slide shows new VirtIO drivers with OpenMP. Tomorrow, Xiaomi people will talk about the VirtIO framework and the network enhancement, but let me introduce very briefly. The new VirtIO framework was introduced by Xiaomi in following a PR and finally merged in this August. And I talked in a previous slide, I was asked to review this price. And initial supported devices were network and block and ARIN, random number generator. And framework is based on OpenMP, which Xiaomi people submitted 90 patches at that time. And it also depends on a new network driver framework as well as IOB offloading. And actually, they made much effort to improve VirtIO networking performance for NuttX. And following chart shows the performance comparison between my driver as of August 3rd and Xiaomi new framework at that time in the PR. So you can find the chart in the PR. And as you can see in this chart, the new framework consumes almost 3 or 4 times memory to improve our performance. And actually, QEMU, VirtIO, and NetX got excellent performance with their new VirtIO framework. However, some configuration were not improved in my environment. And I'm still not unsure, why so some use cases did not show at the speed they expected, but we need further investigation. So before showing a demo video, let me introduce a demo environment and scenarios. So regarding the host environment, I prepared following three kinds of environments. The first one is typical x86-64 machine, so which runs QEMU in emulation mode. Then the others are Raspberry Pi and MacBook Pro, and to run hypervisors, which introduced before as for NuttX. So regarding the network topology, I use a NAPT network address and port translation mode. And as for the demo scenarios, I chose the following command for each. Here, FATFS creates a FAT file system on NuttX. Okay, let me start first demo. So first, checks environment, then start create a file system, and start a QEMU, and check PS and free, and you can see a broke device here, and try to mount. So mount succeeded. And it's mount succeeded. And it checks actual mount succeeded. You can see a MLT and create a file for on the device. Okay. Thank you. And check the cat. So inside the file, thank you. It's and then quit, and then I start QEMU again to check if the file exists, and then mount. Just copy and paste to mount again. You can see actually file exists, and checks actual content. You can see not 2020. Then next checks our networking address. So please move to right hand side more. Please. Good. And and checks actually maybe sorry, it goes back and forth. And it runs iPower, and you can on the and run the server mode on the host side, and this side, so on NuttX, iPower in client mode. Speed is almost 200 megabits. And then start iPower maybe in server mode, I think. And then start the client mode on the host, so Linux machine. So you can see speed also like this, so 250. And then start server mode, and then running QEMU, and checks Telnet D is running, and you can see you can run several commands on Telnet. This is the first demonstration, and so next demonstration shows hypervisor framework on Raspberry Pi. So check first uname and run hypervisor on Raspberry Pi 3 Plus, and you can see VirtIO. And you can check if appears and free, and run a get file number. And you can, maybe you cannot see actual app. 990. And yeah, this is with hypervisor, and you can see several commands. And also, no, please go down. Yeah, actually, you can get 180 milliseconds, very faster than this without hypervisors. And it runs iPower in client mode, and it's running a server on the host machine, and also running iPower with hypervisors. So with hypervisor is much more faster than without hypervisors. And run again when this is server mode, and run iPower in client mode on the host machine. So you will see almost maybe 20 megabits. And you can see iPower on with hypervisor, and then run different port. Yeah, you will see almost double scores as the performance numbers. So with hypervisors, and maybe so this is okay. So last one is a hypervisor on Apple hypervisor framework. You can run NuttX with QEMU on this Apple machines, and PS and free. And you can see as Get Prime is so much faster than Raspberry Pi 3 Plus. And you can see iPower. Yeah, maybe this sorry, but it's okay. So you can see this is iPower in client mode, I think. Yeah. And this one, yeah. Sure. Yeah, it access to a telnet. So in this demo, actually iPower is running on right side, and telnet is running on left side. So both cases are running simultaneously with SMP mode. Yeah, that's all of my presentation. Sorry for, maybe you can see very small fonts for my demo. I'm sorry. Do you have any questions?
Thank you, Masayuki. That was an awesome presentation. Thank you for sharing your experience while you implement the VirtIO drivers. I have a question, but does anybody here have other questions? You can ask him first. No? Do you? All right. Can you talk a little bit more about the motivations to implement the VirtIO? Not on the technical motivations, but what was the primary objective while developing the VirtIO? Was it for debugging purposes? Was it to enable developing devices and applications without the actual hardware? What was the most
exactly. Actually, as you know, so QEMU, so running NuttX with QEMU is very useful to for debugging. And as I said in previous, so last year, so I demonstrated QEMU for a sublet called so quad 9 processor for NXP platform, so which QEMU supports, but it just runs board-specific drivers. But by using this VirtIO, we can run a more widely platform, so such as RISC-V as well. And of course, maybe in the future, we can run the same driver. And if we support the PCI transport, we can run a VirtIO driver on x86 machines as well. But Yeah, actually to run is maybe, how to say, it's easier, but to debug is much more difficult. And it's, NuttX is, as you know, so getting mature, but so running more use case and running on different machines, running on different situations is more difficult and more difficult to debug. So that's why I added these drivers to test more widely, including networking and work devices as well. Yeah, that's why this is technical and my motivation. It's the biggest motivation.
Yes, I see and I understand. I don't know if you agree with me that usually small companies or even individual developers are more used to develop using the actual hardware,
yes,
the boards.
I did it before.
Yes,
yeah, I did it before. Yeah.
What is more common to
yeah,
do?
Yeah,
I think improving this kind of solution, we can develop it without knowing the hardware or even without choosing the actual hardware, and maybe try to get NuttX, to push NuttX into a new level of development.
Yeah.
I think I would say that bigger companies are more likely to use NuttX to develop real products with this kind of approach during the development or workflow.
As you might not know my presentation in 2017, and actually I give some slides for using QEMU as well. So when we developed our other products, of course we actually use real hardware, but for example, for application developers, they might not use real hardware sometimes. So in that case, QEMU is very much feasible and very much useful to debug their application with NuttX on QEMU. Yeah, that's why.
More interesting that we can say that we are moving from embedded software engineering, that is a specific field of knowledge, to a more generalist, a more generic embedded software, not embedded only software engineer. So in general, I would say that it improves for other software engineers that are not used with embedded systems to develop applications using NuttX, for instance, or any other RTOS that is running in an actual hardware, in an actual board or something like that. I would say that it is in that direction, I think.
Yeah.
Do you guys have some questions? People who are...
Is there any comments on YouTube? No?
Not yet.
Not yet. Oh.
Okay, we are planning some quiz for today, but we are near to finish the question. Actually, we just received a question from Andre Almeida. He's asking how much time did you spend to develop this solution? Do you remember in overall, how long it took to get it implemented?
Oh, implementation. So from for all, maybe because this is the first time for me so first I need to investigate the VirtIO specification. Of course, I didn't anything. No, I didn't know anything. So. And of course, I need to check some sample implementation on other platforms like, of course, QEMU and Linux. But it's very, very complicated. So maybe it took maybe 1 or 2 months to understand the whole architectures, and then started step by step. And it actually, maybe 3 months, I guess, to work network drivers. But because network driver is very difficult than creating, developing block drivers. So I worked for, I started as block driver first, but I tried the very difficult part first. So that's why,
Okay, nice. And besides helping to speed up the development of many other things or the drive, did you use it, for example, to investigate bugs or something like that? Did you also use it for help you to find issues in that you could find in real hardware as well?
So you mean, so besides my driver implementation, is there any other issues?
Yeah,
Perhaps I cannot remember, but actually sometimes I found some bugs regarding RISC-V or ARM64. Actually, as you might know, so sometimes my automatic test breaks. And I reported, but it is not VirtIO related, but sometimes, it depends, I guess, But if I found such issues, I soon report it on the pull request.
Okay.